Todo listo.
Great. Excellent. Hello, everyone. Happy New Year's, both Gregorian and lunar years. I wish you all the best for this 2023 or the year of the rabbit. So that's the year in the lunar year, right? Well, on behalf of the co-organizers of this seminar, Rosalía Rodríguez Vázquez de la Universidad de Vigo, Frida Villavicencio de Ciesas, Damián Blasi from Harvard University, Harold Bayen from University of Tübingen, and myself, we welcome you all to the first session of the International Seminar, Language, Culture, and Cognition. Now in Spanish, en español, hola a todos, felices años nuevos, los dos, el gregoriano y el año lunar, el año nuevo chino. Les deseamos todo lo mejor para este 2023 o el año del conejo. Por parte de Rosalía Rodríguez Vázquez, de la Universidad de Vigo, Frida Villavicencio de Ciesas, Damián Blasi de la Universidad de Harvard y Harold Bayen de la Universidad de Tübingen. Les deseamos lo mejor y los recibimos en esta primera sesión del Seminario Internacional Lengua, Cultura y Cognición. Esta vez tendremos al doctor Vito Pirelli della Università di Pisa. Benvenuto Vito al seminario. Siamo molto grati per la vostra partecipazione. Grazie.
Un piacere mio.
Veniente. Harold ha la parola. Harold, you have the floor.
Okay, so it is a pleasure to introduce Vito Pirelli. He is research director at the Institute for Computational Linguistics in Pisa. This institute is part of the Italian CNR, a large research institute similar to the CNRS in France and to the Max Planck Society in Germany. Vito has a broad range of interdisciplinary research interests cutting across cognitive linguistics, neuroscience, information science, computational linguistics. Vito has played a leading role in many projects, including a project funded by the European Science Foundation on morphology named NetWords. Vito and his team have done really wonderful work on modeling morphology with temporal self-organizing maps. But the topic that Vito will talk about today addresses the tracking of reading skills. I first learned about this exciting new line of research at the Mental Lexicon conference last year, and I'm looking forward to learning more about the latest development in Vito's Physiology of Communication lab. Vito, the floor is yours.
Thank you very much for your nice words, Harold, and thanks to the organizers of this seminar cycle for giving me the opportunity of presenting some fairly recent research of mine at my lab, the Communication Physiology Lab that was already mentioned by Harold. So I'm here to present a kind of novel for most of you technology for collecting reading data, especially from early graders, from early readers. But this is a technology actually that can be used by any reader. So actually today I'm going to present most of the data I'm going to present are related to adult readers, since most of the analysis we've been carrying out so far involves adult readers. But as you can see, this kind of technology for its being non-intrusive and particularly ecological lends itself very nicely for being used by early readers, early grade readers. So basically, this technology is finger tracking. What I'm going to talk about in this talk is to show that what finger tracking is an ecological proxy of eye tracking for visual exploration of digital images. And despite the specific motor patterns of fingers, which are completely different from the motor patterns we can find in eye fixation movements, finger movements, we believe, both in isolation and combined with eye movements, reveal important aspects of reading behavior. We suggest, in the end, using figure tracking for continual screening of children's reading development. I will show some data related to this particularly interesting issue, we believe. Okay, first, let us have a look at finger tracking the data. So basically, the protocol that we developed can be described along the following lines. A subject reads a text which is displayed on a tablet screen, and she or he can read it either silently or aloud, while at the same time underlining the words being read with the finger of her dominant hand, which is a common practice, especially for beginning readers, and especially in the scholarly, in the teaching practices here in Italy. The sliding movements of the finger across each word is captured by the touchscreen at a high sampling rate between 60 and 120 Hertz. Touch events, which are captured by the touchscreen of the tablet, are transmitted to a remote server through an internet connection and are used as a proxy of eye fixations to measure the subject's pace of reading. So we are assuming a situation where we have a simple tablet, a common garden tablet, nothing special, a kind of average price tablet, which is connected to our local servers through an internet connection. So this is the kind of general environment we are talking about. Obviously, this is a kind of technology which has some relationships and some strong similarities with the eye tracking technology, but the differences are also quite apparent. Well, we know that eye tracking is kind of traditional, standard technology for measuring, the reading pace, or the reading strategy and processing strategies of a reader, of a subject reader. And through eye tracking, we can record the eye position, we can record eye movements, and we can do that at a fairly fine-grained rate of precision in terms of milliseconds. What can finger tracking offer to compare with this technology? Well, actually, this idea has already been explored in a slightly different context. So in a context of a different task with a slightly different use of the same technology. I am referring here to an influential paper that appeared in Nature Communications in 2019 by Leo et al. And the task in this particular context, they used a tablet and they were showing on the tablet touchscreen an image, a photo, a static image, okay? In this case, it was a photo of a cat, the snout of a cat. And the task was to invite the subject to explore this blurred version of the image. So at the beginning, the image is shown completely blurred, and to explore the image, to investigate its small features by just pointing to with a finger to particular areas of the screen. So the area immediately below the touch, the point to where the touch screen was touched by the finger, was de-blurred, okay? Was shown in its proper view. So the experiment was to explore what particular areas of the screen and what particular areas of the image were de-blurred first, because this kind of evidence could provide some indirect evidence about the visual exploration of the image through eye fixations, okay? So in the end, the experiment was intended to measure the correlation between the finger touch events on the screen and the fixation points of the eye in exploring the same screen, in the same scene, the same visual scene. Okay, and these are the results, very encouraging and very nice in these experiments. So here we have what areas were fixated by the eye, and these areas were highlighted in different shades of color on the left-hand side of the screen. And then we have the similar patterns of touch events on the screen, where the same image was explored through the technique known as deblurring with a finger. Okay, you can see there is a high correlation between the details of the image of the cat that were fixated by the eye compared with the same details that were deblurred through the finger tracking exploration technique. The correlation was considerably high. And this represents a sort of basis that you can use the finger, or you can use the finger movements as a kind of proxy of the eye movements in exploring a visual scene. One of the most striking results were connected with the exploration of the same scene by subjects with autism spectrum disorders. Okay, you can see how an autistic subject explore the scene with a finger on the left-hand side, of this screen, and you can see how control subjects explore the same scene with a finger. Okay, you see this kind of noise avoidance strategy, eluding completely the single feature or the single trait of the faces of the subjects that were portrayed in, it was basically the same photograph in both contexts, in both tasks. And you can see the noise avoidance strategy of the faces of the two subjects by subjects with autism spectrum disorder, and the opposite strategy, where most of the fixation, most of the finger points were focused on the features of the faces on the right-hand side. Okay, showing that this correlation is strong, it is reliable, and it reflects, even some sort of atypical behavior in the visual exploration of the images. Okay, so what's the relation with the reading task as we conceived it? I mean, we are not talking about actually finger pointing to particular areas of the screen, but fingers gliding across lines in a reading text. The protocol can be described as follows. A child is asked to use a tablet as a reading book. While reading a text, a child underlines the word she's reading with a finger of her dominant hand. Finger movements are captured by the tablet touchscreen, encrypted for reasons of privacy and data protection, and then sent to a central server for an internet connection. Here, data are post-processed, time aligned with the text and the reader's voice when the subject is reading aloud, and analyzed these patterns, these movement patterns in terms of direction, path, speed, and are correlated with the linguistic features of the tracked text units, linguistic features that can be syllables, words, or phrases of the text being read. In fact, this is a kind of integrated multimodal platform, which whereby we are trying to correlate signals from different sources and which are aligned along the common timeline. And in fact, the kind of data we used are audio recording data, in the case of aloud reading, finger tracking data, also the reading comprehension, and also the linguistic features which have been pre-annotated in the texts being read. Okay. Concerning these levels of annotation, we apply to the text. Obviously, this information is not displayed on the touchscreen. It's not part of what the reader sees or looks at while you're reading on a tablet. But this is something, this kind of information that we keep in the background and that we correlate with the pace of reading of real subjects. And we have several levels of annotation. And so you have to think about this as a kind of layer, as a kind of stack of different layers of information which are aligned along the common timeline. And this information concerns, starting from the top, the audio recording, the finger tracking patterns, the actual text layout against which the finger tracking patterns are aligned, and then all sorts of linguistic information, and then the content of the text proper. Okay, this is the kind of information we are trying to relate. And by correlating this kind of information, which again, I repeat, are aligned along the common timeline, we can learn a lot about the reading skills of the subject being tested. Okay. In fact, the kind of levels, the kind of linguistic levels of annotation we are adding to the text, they are translated into some kind of readability scores. There is another group in our institute which works on this particular task, which requires, neural network classifiers which are trained on pre-classified text in terms of easy texts which are easy to read, texts which are more difficult to read. And basically what this type of classifier does is to relate the linguistic features of the text, which have been already automatically annotated, with some scores, readability scores, which reflect how difficult or how easy either the single words or the single sentences of the text is. And these are reflected by these different shades of colors here in this column here, but which are actually just a visual representation of levels of difficulty of a text. So we can have a particular word which is rare, which is morphologically complex, as annotated as particularly difficult, or we can have an entire sentence which has been annotated thanks to this kind of dependency syntactic annotation, which is shown on the left-hand side of the slide. We can see that sentence is particularly complex because, for example, the subject is separated by the main predicate by different words, for example, by a WH clause or something complex embedded between these two units and things like that. So you have to imagine that behind the text, we have this huge level of annotation and these readability scores, which are associated with certain units making up the reading text. Okay, then we also test with the same kind of device on the same tablet, also the reading comprehension of the subject. Upon reading a single text page, the screen of the tablet refreshes itself and shows some multiple answer questions concerning the content of the page of the text that's just been read. Okay, so what the child has to do is to click one of the options, one of the multiple answers which are shown here in the bottom half of the screen by ticking one of the possible alternative answers. And one possibility which the reader can avail herself of is to scroll the text. You know, the top half of the screen, you have the text shown here, and this is a scrollable text. So the reader can actually look for the information which is asked in the bottom part of the screen. Okay, so we can check also the level of comprehension of the text being read through this simple question answering session, you know, after each page of the text being read. Okay, this is a kind of session of a kind of reading session which has been recorded on an adult reader. Actually, she's my daughter, reading a particular text. And then we have a rendering of the pace of reading. There you see a video recorded on the right. You have a kind of animation showing the digital rendering of a pace of reading on the left-hand side of the screen. Okay, I'll start this session. I hope you can hear the audio because we have also audio recording this.
Mio nonno Andrea è molto bravo a raccontare le storie. Non racconta le storie della buonanotte. Il nonno Andrea non legge quelle dei libri. Racconta storie che si inventa al momento. Mi piace molto ascoltarlo.
Okay, this was just a very short cut of the whole file. I mean, I only highlighted the first paragraph of this text. But by going through this kind of digital rendering on the left-hand side, most of you have realized that we are highlighting the words in yellow. Actually, it's in shade of yellow, so you can see that better in the next slide. We are highlighting the words as they are read because we are aligning the audio file with the finger tracking thing. And we are also showing exactly on the screen where the finger, the index finger, is pointing to at each time step, at each time tick. So we are synchronizing this level of finger tracking with the audio, and we are aligning both time signals with the text being read. Okay? I hope this is fairly clear because, I mean, this is a kind of very important, it gives you a kind of very important, very concrete feeling of what we are actually recording and the way we align this data. Okay, here I just started a session, a reading session with a third grader. Okay, the pace of reading is very slow. It didn't start yet. Yeah, it's just starting now. And you can say the blue circle, which represent the point where the finger, the point on the screen where the finger is pointing, while we are highlighting the words being pointed to. Okay, you see there is a difference, there's a displacement in between the text being underlined and the points on the touch screen where the index finger is pointing to. Obviously, by underlining the text, we are not pointing straight on the text, but we are displacing our finger a bit below on the text. So most of the problem is how you align these two signals. You know, the text, the layout of the text as it is arranged on the touch screen, on the page displayed on the touch screen, and the position of the finger relative to the reading lines, relative to the actual text. You can also see where the most difficulties in reading by this child arise, because you can see it displayed in different shades of colors, ranging from yellow to red, how quickly the child is reading each particular word. So if the word is highlighted in yellow, that means that the child is reading that word fairly quickly. If the child is hesitating or is regressing to the same word, or is pointing, spending a lot of time on that word is highlighted in red. And you have the whole gradation, you know, from yellow to red as a kind of visual representation of words which are particularly difficult. For example, this macchine, which is this deeply red word, I mean, for some reason, basically because of the construction where that particular word is embedded, macchine means machines, or in this particular context, it means cars. I mean, it's not a particularly rare, complex word, but because of the context where the word is used, I mean, apparently this child found it very difficult to read. Okay? So this is basically the end of this section. I hope I gave you the feeling of what we are doing, okay? The basic results and the basic kind of evidence we can extract from this, through this technology. Actually, sorry, the technological hurdles that we have to overcome, I mean, we're not that trivial, in spite of the evidence and the, say, ecological naturalness of this data. Let me highlight here some of the basic differences between eye reading movements and finger reading movements. We know that eye reading, the kind of signals we can, the kind of data we can extract from eye tracking consists in fixation duration, scanning path, fixation rate, and skipping rate. But basically, I mean, the main feature of this type of data is that they are discrete signals, because we have fixations which alternate with saccades, right? Here, the pattern of data that we can extract from finger data are inherently continuous. As the finger is gliding across the lines of the text, and because we have a high rate of sampling of these movements, we can actually extract very detailed information and time-bound and time annotated information about the position of the finger at each character in each reading word. So we can measure here how continuous the signal is, since the signal consists in its gliding movement. So we can measure the tracking time, the tracking path and direction, speed variation, and the most prominent difference between this type of signal and the eye tracking traditional signal is that we have little skipping. Since we have no saccades here, we have little skipping or short or functional words or highly predicted words. Okay. The only thing that we can note, or the only evidence that we have supporting a kind of skipping behavior with the finger, is the finger is speeding up on particular words. So it's going through a kind of a burst in speed. And I will see you some data showing that this is the case. Okay, just to show you that this is not a trivial problem. The problem of alignment of the finger pads on the page and how we can align this sliding movements with the text is not trivial. And actually we can have, well, this is a somewhat extreme example of a particularly erratic path of figure tracking. But we managed to do the alignment with the text in a fairly successful and robust way by using a mixture of available technologies for solving this task, which is a mixture of time warping and convolutional algorithms, which are solved through neural networks. So there is a considerable artificial intelligence technology behind the solution of this tricky problem, which has some similarities, but also some differences with the problem of aligning, the eye tracking with the text being read, the eye tracking records with the text being read. I don't have time to focus on this particular aspect. So these are the basic difference between the discrete and continuous signal of the same text. Okay, false colors, shades of colors show which words have been read more fast, more quickly, which words have been read more slowly. So red points mean slow reading time, while yellow segments, yellow lines mean quick reading times. Okay, and you can see that why we have these pointwise fixation patterns on the left-hand side for the eye tracking, we have more continuous sliding movements for the finger tracking thing. Okay, and here I highlighted, a very short excerpt that shows that basically there is a high correlation between the alternation between red and yellow segments in the two modalities. Although in one modality you have pointwise evidence, just fixation times, while in the other you have sliding patterns, so continuously varying speed rates. Okay, one thing that a little surprised us is that if you just look at the time it takes for a finger to slide across a word compared with the time an eye takes in fixating the same word, on average, eyes take longer to fixate words than fingers to slide across them. So the pace of sliding across the text is quicker than the pace of fixating them. Well, there is an intuitive reason. If that sounds a bit paradoxical to you, there is an intuitive reason for that, is that the eyes make most of the processing effort, while the finger is not making any processing effort. It's just trying to follow the path at the speed of the fixations and the processing carried out by the eyes. So basically the fingers are some sort of pacemakers, and they are almost nearly or very closely synchronized with the rhythm of our reading aloud, of our articulation of the text being read, either covertly in reading aloud or overtly in silent reading. Okay, that's the basic thing. But in spite of these differences, the correlation between the token level fixation times and token level tracking times is remarkable. So you have, well, different correlation scores between the two kind of modalities. In aloud reading, you have higher correlation between these two signals. In fact, we are including here only fixated words. If we included also skipped words, then the correlation would be considerably raised. So I'm showing the worst case of correlation, where we are including and counting in only fixated words. So you see here the correlation between the times of fixated words with the times of the same words which have been finger tracked. Okay, but the interesting thing is that if we move from the token word level to the chunk level, where chunks are basically non-recurrent syntactic phrases. Some sort of very simple, non-recursive syntactic phrases. Okay, if we move, so it's a very flat, simple level of syntactic annotation. So if we move from the token level to the chunk level of annotation, the correlation increases considerably. And the two signals are almost completely synchronized if we move to the sentence level of correlations. So correlations here are are amazingly high and consistent. Okay, that means that overall, the time is taken by an eye to go through a text to a sentence for reading is the same or is highly correlated with the time that the finger takes to slide across the same line of text at the sentence level. Obviously, there are differences, and some basic differences given and is explained because of end of the line saccades. Okay, for a finger to move from the end of the line currently being read to the beginning of the following line, I mean, it takes nearly 1 second. The movement of the finger, something on average like 800 milliseconds. While for an eye, moving from the end of the currently read line to the beginning of the following one, it takes just a few tens of milliseconds. Okay. So basically, the idea that we have is that the finger is trying to chase the eye, and that's the reason why it goes fairly quickly, through the words. It tries to chase the eye, but then once he eventually manages to reach the eye at the end of the line, the eye goes ahead again while skipping through to the following line. So that's the situation you have to imagine. Okay, here I put it together some data which are related, although I won't have time to explain to what extent, but the data about the difference in terms of voice span in our adult reading data. And we correlated this evidence of the eye's voice span. This is the distribution of the eye's voice span, and we compare with the same kind of evidence that came from a influential paper by Laubrecht and Kliger on the sentence reading and the behavior of the eye voice span in sentence reading. I mean, the patterns are almost identical, although we are focusing here on eye tracking data, not on finger tracking data. Finger tracking data is slightly different. I could not show it because we are still processing, and we wanted to make it sure that the patterns are correct. So I didn't dare show it that. But the interesting thing is that at the level of the eye voice span, our data correlate quite strongly with the evidence that was provided in the Laubrecht and Kliger's paper, with the only difference that the only difference lies in terms of the time span, because our average time span between the time at which the eye voice span is the difference between the time at which a word is fixated and the time at which the same word is articulated in reading aloud. So there is a difference in terms of milliseconds, in terms of time, but also in terms of spatial span, between the location of the two events on the reading sentence. So in terms of space, the eye voice span is identical, and is between around the 15 letters. Okay, so the eye is ahead of the voice of about 15 letters, 15 characters, 15 boxes. Okay, and we see the same result in both the types of evidence. Why there is a difference? So we replicated the same kind of results that were presented by Laubrecht and Kliger. The main difference is in time, because in our case we have an average difference of 800 milliseconds against a difference of 600 milliseconds in Laubruck and Kliegel paper. Well, we believe that the basic difference, since the difference in thermal space is non-existent, since we replicated the same result, the difference is in the pace of reading. Obviously, reading a connected text is faster than reading a single sentence shown in isolation in a kind of control condition. So in a sense, our data reflected the evidence about more natural reading condition as in the task we proposed, in the ecological task we proposed in our subjects, which is the task of reading a connected text. And reading a connected text probably reaches a high speed rate than just reading a sentence in isolation. Okay. Well, basically, I can anticipate, although I could not show the plots actually, that the finger voice span lies in between the eye and the voice, and the difference is much shorter. Is a few characters, is a few letters, and it's a few hundred milliseconds. Between 200 and 300 milliseconds. So we have an advantage of the finger with respect to the point in time where that particular word is articulated of about 200, 300 milliseconds. So in a sense, this clinches the argument that I was suggesting earlier, than the finger is a kind of pacemaker and is following the rhythm of articulation. And this is why it's very close to the voice onset of each particular word. Okay, what we can do, what kind of information we can extract from our data? Do I have 10 more minutes? Okay. Well, basically, we used this data, for example, for assessing a developmental issue concerning how children with different years, with different grade levels, actually progress in make progress in their reading skills. And we measure this kind of progress, in terms of decoding accuracy, which is the plot that you see here on the right-hand side. Actually, you know that Italian has a fairly phonological orthography. So it's fairly easy to start learning how to read Italian because we have this kind of nice almost one-to-one correspondence between letters and sounds. So it comes to no surprise when you look at the decoding accuracy at the word level, that, even at the lowest grade level, which is the third level in this sample that we consider, we have very few errors, or we have, a preponderance. The vast majority of words were decoded in an accurate way. Obviously there is a progress here. So the number of wrongly decoded words decrease with grade level. But still, we have a good, level of decoding accuracy when it comes to words. But things are slightly different when it comes to nonce words, so to made-up words, which means that there is a lot of lexical, reading, even in a fairly orthographic language, like orthographic script, like the Italian language, which would probably favor a kind of syllabic strategy. Here, the strategy at the very beginning of reading skills is anyway token-based, word-based, rather than syllabic, as the nature of the script would, in a sense, suggest. Okay, and we have similar kind of evidence concerning reading fluency. So the speed rate, obviously we have a difference between reading and oral. So, these different shades of colors highlighting different levels of proficiency of reading. We have the two basic levels, which are 1 and 2. Then we have 3, 4, which are intermediate. And then we have 5 and 6, which are more advanced levels. Obviously, there is a progress. The progress is significant, both at the level of fluency, meaning the level of speed at which words are read, and at the level of comprehension that we tested through our question answers. Oh, here we have some interesting evidence concerning reading and autism, which has recently been published based on data that were collected with our tablet. And we have, linear models here of the correlation between the time, the reading time, and word length and word frequency for both ASD children with autism, and control subjects. You can see here that the influence of the correlation between both the positive correlation between reading time and word length, and the negative correlation between reading time and word frequency is more prominent in ASD children than in TD children, suggesting that probably the orthographic lexicon, which is learned and which is which has been accumulated, through progress, through the process of learning to read. I mean, is developing more slowly in ASD children than in control children. And also this is confirmed by this kind of more developmental data, where we divided the same kind of correlations by the age level, grade levels. And we see that while we have in control children, yes, in normally developing children, a kind of jump between the third grade, between the second grade level, which is the entry level of reading skills, and the other levels, we have a big jump here, meaning that the child is learning more and more rarer and longer words. Here, the development is more slow and is more gradual, suggesting that ASD children adopt a more syllabic strategy, so a more compositional strategy rather than an holistic strategy, as normally developing children are doing, which is a kind of interesting evidence, concerning the cognitive, the spectrum of cognitive skills, which are normally associated with children with disorders of the autistic spectrum. Okay, maybe I overestimated my time, so I won't have time to deal with this second slide developed by associated with data of ASD readers. Okay, I want to go very quickly through this interesting analysis between the movement of the fingers and the movement of the eyes, because this gives you a kind of background explanation of the kind of evidence I was showing at the beginning of this presentation. So we know from the Braille literature that finger movements go through continual alternating phases of finger positive and negative acceleration, punctuated by reversals of direction. So this are the typical patterns of readers which are engaged in Braille reading. Mean velocities and degree of intermittency are similar across forward and backward, but the most important feature that I would like to draw your attention to is that the rate of alternating positive and negative phases increases as the finger slows down. So we have this kind of burst of differences in the speed of finger when this finger is slowing down. So the more bursts and the more alternating patterns of velocity we see, the slower the finger is going through a particular text pattern, say a word. So this is an interesting fact because it was confirmed by our analysis of the speed in either content or function words in both allow the sign and reading. Content words show a slower speed in terms of letter per second compared with function words. And this pattern is replicated also in silent, although the speed is is higher, obviously, in the silent reading than in the loud reading. Okay. And also speed variability has some difference across the same kind of data. So the idea is that by detecting this kind of local bursts, local variation in speeds, which are pictured here and highlighted by these blue points here in this graph, we can try to correlate these bursts here with the fixation points of eye movements, okay? And this is shown here on a short excerpt of this sentence. And you can see that there is this high correlation. So we can assume, by looking at the tracking movements of the finger, we can assume that there is a fixation on this particular word every time we see this particular burst in these patterns of speed of the fingers, okay? And we try to build a simple predictive model based on this type of intuition. And results were interesting. They were shown by this table, where the accuracy in guessing whether a word is predicted or not is, whether a word is fixated or not, based on the predictions that we can derive from our speed burst by looking at the finger patterns of movements. We can achieve a precision in this prediction task of, you can see, 0.89 and a recall of 0.84, which makes a nice F1 score of 0.86, which is fairly high and higher than any other prediction algorithms that we could find in the literature concerning the eye fixation. So finger movement, speed bursts in finger movements can be a nice approximation of fixation points in the eye tracking reading. Okay, then a final point about other possible analysis of these dynamical patterns that we carried out with a particular technique which is used to measure the level of determinism of dynamical system, which is called recurrent quantification analysis, which basically aims at finding the levels of repetition for some text units, which are arranged on the same text is arranged on the horizontal axis and the vertical axis of this square matrix. And then we have a point here whenever we have the repetition of an event along the two texts. These are the same texts which are arranged differently, vertical. And so whenever we have a repetition, for example, the word round here is repeated, you see here, is repeated here. So we have another point here and is repeated here. So we have 3 repetition and 4 repetition here along this vertical axis. So we can measure by these recurrent quantification techniques the amount of determinism, the amount of repetition in text patterns. But in our case, we are not measuring text, words which are repeated, but time patterns in figure tracking which are repeated. So when a particular word is finger tracked at the same speed as another word in the text, we have a point in this kind of diagrammatic representation. Okay, and we can find pattern of determinism and we can count them along these diagonals. And if we calculate the pattern, oh, you can see how the time onsets, you know, the speed, the finger tracking time, and in both adults and children vary along our texts. This is the timeline of the text on the horizontal axis. This is the time taken for each word, you know, in terms of figure tracking time of this text. And we see in red the patterns of variation in children, and they are very dramatic. You have a lot of variation across words. While the patterns of variation of adult reading are existing, are there. There are some, you know, bursts here of variation in terms of reading time, but most of the time they are repeating along, you know, a narrow range of variation, and these are counted as a kind of repetitions in our metrics. Okay, So you can see that determinism is what counts in reading development. For example, we measured here levels of variation of determinism along, finger tracking patterns for different subject groups, for ADS subjects, for third graders, for fourth graders, 5th graders, and adults, and the amount of determinism increasing in both aloud and silent reading. And the nice thing is that if we look at the same patterns of determinism by exploring eye tracking patterns as opposed to finger tracking patterns, we see exactly the same picture, meaning that, again, finger tracking could be considered a kind of faithful proxy of eye tracking data. Okay, I'm making my concluding remarks, hoping I did, speak for too long. Concluding remarks are that in our view, this finger tracking technique is at the same time simple and powerful. Simple because it is relatively technologically simple, noiseless, robust to variation, and cheap because it can be captured, it can be implemented through a simple internet connection and a common garden tablet. And through this kind of simple technology, finger tracking can offer ways of monitoring reading development at scale by gathering data on a large scale. This kind of data I was showing were collected in a few weeks. We managed to collect something like more than 400 subjects for children and 100 subjects for adult readers. Using highly within a highly ecological reading task, which was connected test reading, as opposed to just word naming or reading sentence reading in isolation. Its fine-grained information, we believe, can provide reading skills at both population and individual level. The time-bound analogical signal of figure tracking makes it possible to observe very fine-grained dynamic processing effects. And finally, we are currently experimenting with the usage of our tablet in clinical contexts, where finger tracking combined with AI technology, especially in connection with speech processing, can offer unprecedented opportunities for reliable, efficient, and non-invasive screening of specific learning disorders. And this is basically the end, with a kind of snapshot of all the people that contributed to this nice project, which is, closing to an end in 2023. Thanks a lot for your attention.
Great, bravo, Vito.
Thank you.
I'm sure people are cheering you. I mean, it's a pity we don't have the faces here. At least mine is not here, but I'm really happy to this. So Harold, would you like to open the floor for questions, or should I just continue?
Why don't you continue? I have some questions, but...
Yeah, okay, so let me... this is very exciting, Vito, really is. You open the possibility not only technologically to a myriad, tons of studies, interesting studies on different populations and all this. I'm sure you have been presented with this question before, but let me ask, I have this question, very general, very ontological, if you want. I mean, it's just, I just want to elicit your reaction. So obviously reading, our brains didn't evolve for reading in the first place, right? So this is a rather secondary skill of humans. So writing systems appear, as we know, very, very recently in the history of humans. But then let me just play devil's advocate, because even though if this is true, I mean that writing is a really recent skill, we also know that engraving or making marks in stones and caves is rather old tradition of humans. So what I'm trying to say is that writing systems evolved. Already full-fledged writing systems are recent, but this skill of engraving or painting can be traced back long back. So what's your reaction of this, about this possibility that writing or representing things visually could be something that humans are acquiring as a really embedded in our brains during the evolution of our species? So what I'm trying to say is that it's not that artificial, the writing and reading. And it seems to me that your study or your agenda is pointing out to this. Well, it's not a pun. So this pointing is previous to reading, to the observation. I mean, pointing is more general across cultures, across humans, even other hominids point. I mean, as we know, chimpanzees, bonobos, gorillas can point. Even dogs can follow our pointing of extremities and so on and so forth. So what's your reaction overall? I mean, I'm not even posing a question. What's your reaction about this skills of reading and whether or not cognitive systems of modern humans are adapting to these new skills? What do you think?
Well, my first reaction would be that your question reminds me of Dan's theory of recycling, areas in our, cortex for reading that were initially evolved for completely different purposes. Like, for example, identifying small objects, and that were the areas that were eventually recycled for identifying and telling different letters, arranged according to different patterns. But so my first reaction is that, there is some grain of truth in that, and probably the kind of evidence we are exploring, the kind of evidence we are providing, pointing in the same direction. You're right. I mean, the movement of the handwriting, for example, the movements have some deep connections with, generally speaking, the movement of our fingers, this kind of motor patterns that are strongly ingrained in our cognition, and thus reflects, in some sort of instinctive ways. I mean, you were mentioning the act of pointing as an act of focusing our attention in a particular direction. And this is also related on this teaching strategy that I mentioned at the very beginning of my talk, of attracting the child attention to the spatial patterns of spatial arrangement of letters, which are arranged from if the direction of our reading is from left to right, going through with a finger through a line of reading, I mean, is instrumental in trying to attract the attentions of the child of the time order characters aligned on the page. Okay, this means that this kind of movement is fairly natural, because this is a kind of attention attractor of the child, and these in somewhat connected, although the movement patterns are deeply different from, for example, from eye movements. And although I emphasize that the finger is apparently playing no role in terms of text processing, because obviously, especially in adults, I mean, in early readers it's different, because do you remember the animations I was showing where the children had some particular troubles with a specific word, and he keeps returning to the word and underlining the word repeatedly, several times. So that means that actually, in that particular case, the child's finger was not chasing the eye, but actually was trying to guide the eye. So we expect some sort of slightly different patterns in the correlation between finger movements and eye movements in the child, when compared with the same kind of patterns that we observed in the adults. I don't know. This is a kind of, I mean, I've touched several things, but this is only remotely connected to this question. But you made me realize there's some patterns of our behavior, like, for example, the motor patterns of our fingers are deeply ingrained in our cognition. And so it is eventually not surprising that these movement patterns correlate quite highly with the movement patterns that we observe with the eye tracking technology that are more intimately and more strongly connected with our processing strategy in a kind of immediate way. But the fact that the fingers, in a sense, can reproduce the same kind of patterns in a surprisingly faithful way means that this kind of connection between movement patterns and cognitive costs of our processing efforts are strong, in fact. Probably this didn't reply to your question, but your question made me think of this kind of issues.
Great, thank you very much. You're on, Harold.
Okay, yeah. Thanks a lot for a beautiful talk, Vito.
Thank you.
The impression that I am getting from your talk is that actually your finger tracking data is much richer and maybe much deeper than the eye tracking evidence. So if looking at what you present, it looks like the eye is very quickly scanning. There's a lot of information that's captured in one fixation. It then moves on. It tries to quickly explore the lay of the land, so to say. But you get very little information about the contact that this information makes with our knowledge of what words sound like, how you articulate them, and so on. And it seems to me that your finger tracking data shows that there is much more contact made with the internal, say, targets for articulation, or when people actually are speaking out loud, that you might get much closer to the knowledge that we have of what words sound like. Is that a reasonable interpretation? Because it looks to me like a bit like you're very defensive, like your thing has to do what the eye tracking people do. And I'm beginning to think that your data are at least equally valid as the eye tracking data, and might even be more informative. So it could also even be interesting to, as it were, take the eye tracking data and try to subtract that out of your finger following data, so that you get an even better image of better insight into what is going on, with the real understanding also of what words sound like, how you speak them, how you integrate them, all the co-articulation that's going on between words, and so on and so on. So some wild ideas, but I'm curious what you think.
Well, I think you're right. I mean, obviously, when I've been presenting this stuff, probably for the first time to most of the audience I've been addressing, over the last year or so. So I made a special effort to win their hearts in connection with the kind of technology we were developing. So we were trying to persuade that what we are producing, what we are offering, is a kind of reliable evidence in comparison with more traditional, well-established knowledge like eye tracking technology. But in the end, I think you're deeply right in pointing out that the kind of movement patterns that we are capturing through this fairly simple but surprisingly rich and powerful technology are very informative, and probably more informative than just the patterns of eye fixations that we managed to recall through, for several reasons. Because they are more robust, because they give you information about handedness, which is something that, especially with clinical populations of hyperactive children or autistic children, is something very important, because it is deeply related with their cognition. And then, because of the patterns of movements are continuous, we can monitor, the processing strategy of the reader and its deeper connections with either covert or overt articulation. So you're quite right. I mean, it was a pity I couldn't show, but I didn't want to show too much, so I didn't, work very hard in order to extract this data. But the patterns of the finger-voice span are extremely correlated, which means that, in fact, I mean, concretely, the finger is keeping the pace of our either covert or overt articulation. This is exactly what he's doing. And is at the same time keeping track of where we are in the voice in terms of the visual organization of the text image. So, for example, it's keeping track visually of the fact that we are, say, one word behind the fixation point of the eye. Okay, so if there is something wrong, the eye can regresses to that point and resume processing, for example. So in that connection, actually the type of information which is provided by the recording of finger movements is much richer. Also in terms of variation in speed, which is very important. You cannot see variation in speed in eye movements because you have either fixation points or saccades, while you can have continuous variation in speeds while going through, a text for reading it. And we have evidence of these at the level of chunking, so at the level of consecutive words which are chunked together in a kind of shallow constituent. And you can see how the finger speeds up, and then slows down, initially speeds up, and then slows down when he finds the last word of the chunk, which is the most contentful and informative word of the chunk, okay? And you can see this also at the level of word, since, because of the sampling rate is very high. You can see how you have a raise in the reading time in a morphologically complex word, more or less at the word boundary. So we have some kind of preliminary evidence that you have a slowing down of the speed of the finger, where when the finger is crossing the boundary, say between the most contentful part of say the root or the theme of a verb and its inflectional endings. So you see this kind of slowing down of the finger while the finger is going through this kind of I know you don't like morphemes, but we can agree that there are some kind of gradient transitions between internal lexical constituents. We cannot call morphemes, but we have these kind of transitions, which are more connected with probably uniqueness points, some other criteria for identification of internal constituents. But we can see these effects while looking at the speeding variations in figure tracking movements. So I agree. I mean, you're on the right track, but preliminarily we have to show that these data are coherent and consistent with the eye tracking evidence. Yes.
Do you have any information? So I don't know whether your resolution is fine enough, but if you have the audio, so you could do some forced alignment and get phone durations out.
Oh, right.
Yeah, and it would be interesting to see whether you have enough resolution in your finger tracking that you can see something of a kind of maybe a bit smooth, but if you have a long vowel versus a short vowel, or you have a long plosive versus a short one, that might also show up in your record.
Okay, to put it shortly, I don't have evidence of this kind right now, but that if that were true, I mean, it was fairly consistent with the general intuition that the finger is a kind of pacemaker of the overt articulation. Okay, in that respect, yes, I could expect something like that to be observed to eventually happen. At the moment, we are just trying to address kind of more trivial issues, right? For example, the automatic classification of how accurate the decoding of each word in the text is, because that would be a huge help for, you know, for clinical testing of and also for assessment of the reading skills of a child. I mean, at the moment we can align the audio recording with the text, so we know exactly when a particular word is the onset of the voice in terms of time at any particular word in the text. We can say to what extent that particular word was easy to recognize. But one thing that we cannot do with the available technology is whether that particular word was pronounced accurately enough or not. Because, you know, all these kind of formidable AI algorithms for speech recognition tend to normalize, you know, tend to, overemphasize recognition, you know, in terms of their language modeling. And they are not able to spot the accuracy with which a particular word was actually pronounced by a reader. So we are just struggling with these more trivial problems. But I think eventually our interpretation of the figure tracking movements as some kind of pace keepers or pace makers of our articulation is true, then we should be able to observe the kind of effects you were hinting at. Yes.
Yeah.
That's great. So along the same line, so I was thinking about intonation or prosody, because I mean, just by glancing at your figures, so I saw that the fixation was in stress words, I mean, content words like this. So the finger knows it's grammar, right? Pretty much.
Right. Well, that's a very good point. That was related to one of the slides I was not showing to you. I mean, I was showing to you, but I did not talk about. And you know, there is this problem of intonation with autistic children. They apparently lack any type of intonation. They have this kind of flat intonation, okay? And we thought about ways of capturing this kind of effect. And we eventually found some way, because we were looking at weak punctuation marks, you know, like commas, semicolons, colons, that kind of stuff, okay? And we look at the speed with which autistic children go through these weak punctuation marks, compare with the speed with which typical readers go, okay? So the idea is that if you see, I mean, punctuation marks are sort of prosodic markers, in a sense, or orthographic correlates or some sort of prosodic markers. So you expect to slow down when on a word if it is immediately followed by a comma, okay? That's your expectation. That's your natural pace of reading. I mean, if you keep the intonation, you expect, you know, your reading speed to slow down on a word which is immediately followed by a colon or a comma, something like that, okay? We did find this kind of slowing down in typical readers. We did not find this kind of slowing down in autistic readers. And that's a way of nicely correlate, you know, variation in speeds with intonational information. Although that was analyzed only on the basis of orthographic evidence and correlation of finger tracking movements with orthographic evidence, with the presence or not of punctuation marks. We did not analyze, you know, the contour profile of the audio signal.
Wow, that's interesting. Thank you. So do we have some questions on YouTube, Sergio? Hello, Sergio?
Yes, there are a couple of questions. So first of all, thank you very much, Dr. Pirelli, for an interesting and thought-provoking presentation. And the questions would be, well, the reading task was always done aloud. Is there any evidence of any contrast based on whether it was performed aloud or silent?
Actually, probably that makes me think. I didn't make myself clear. Actually, we captured evidence of finger tracking and also eye tracking data in both tasks, both reading aloud and silent reading. So both in oral reading and silent reading. And actually, one of the added value of using finger tracking is that you can sort of monitoring the pace of reading, even if you have no audio signal where you can measure the pace of reading, reading aloud. So yes, we have this evidence, and this evidence, by comparing this type of evidence, I mean, things go in the right direction. So silent reading is much faster, or consistently faster than oral reading, and there are all sorts of interesting differences that we normally find in the literature.
Nice, thank you. So the next question would be, could we correlate difficulty of reading with linguistic complexity of the text?
Yes, at least we expect so. I mean, there is some evidence, although it is still unpublished, that we have a correlation with some sort of complex, fine-grained linguistic features. I mean, in terms of readability scores that I was mentioning in the first part of my talk. Obviously, we found the obvious benchmarks, in connection with, for example, the speed of reading in connection with linguistic factors like word frequency or word length. And we had the expected correlation, meaning that, shorter, more frequent words are read more quickly than longer and less frequent words. So we managed to find this correlation, although these are yet unpublished data. And the interesting thing is that we find these expected correlations also by with higher level linguistic features, like, for example, the complexity of a sentence, or at the level of syntactic embedding, or at the level of dependency relations, for example. We have evidence for that.
Okay, thank you. A couple more questions. Well, pushing the study a lot, what would or could happen with an assignment where the language that must be read is a non-natural one, like, for example, math or computer code or something like that?
Well, certainly this kind of technique can be applied also in those contexts and to these particular tasks. I'm not sure I got the point of the question. So what I would expect, or if this is applicable, okay.
Yes. What would you expect?
Well, depending on the type of I'm not direct experience, in the sense that I didn't try this particular task or this particular. One thing that we tried, and one thing we are collecting data for, are by confronting a reader in a L2 language, so in a foreign language he has learned only later in his or her lifetime. So this is something that we are experiencing, and we are experimenting right now. And generally speaking, what we expect is that we have stronger effects of frequency, of word frequency, on the time reaction and on the naming time of people when confronting with the L2 language compared with their native tongue, with a mother tongue. And this is, the classical pattern that is expected, that is found elsewhere in the literature. And we have evidence that we can replicate these patterns. Concerning our other types of texts, or other types of languages, like artificial languages, or I'd rather not comment on that, since I have no direct experience. And I mean, the range of variation is too huge to make some sort of sensible generalization.
Right, thank you. And one last question. are there any other applications for this method outside of the study of reading development? I'm thinking, for example, with the acquisition or learning of sign languages.
That's an interesting question. That essentially relates to the issue. I mean, it's a completely different issue because I've no experience of some sort of graphical representation. A graphical, actually, this is something that eludes my knowledge and my competence. If there is some sort of script-like representation of sign languages, or whether there is no point in making any such of invention, since deaf people can easily read the normal text. So I cannot see, I'm afraid, I cannot see any obvious connection between this type of technology and sign language, because the only relationship, or the only possible connection I have in mind, is concerned with static images and the exploration, the finger exploration of static images like photos or things like that. While in the case of sign reading, I mean, movements, play a fundamental role. So I can't imagine of any sensible way of exploring, animations of videos through the fingers. I find it hard to make any kind of possible association with this kind of application, because images must be static in a sense to be explored by our finger tracking strategy, as it were. And even though the alignment of characters have an obvious connection with time, it's simply a static image of a page. So yes, my answer is that I cannot make any straightforward connection with the exploration of sign movements through finger pointing. I cannot imagine anything sensible like that. Concerning the applications more generally, the applications of this type of technology, I think the applications are extremely promising, and they range from education to diagnosis of specific language disorders, for example, or specific learning disorders. There is a huge range of areas in which this kind of very handy technology can be applied. And actually, we made an application for applying this kind of technology through the task of reading to subjects with early cognitive impairments. But this is a kind of project proposal that we hope will be funded in the near future. We hope we will hear some good news in this connection soon.
Thank you very much.
You're welcome.
Great. So, Hal, do you have something else?
I have one more question. Vito, have you ever looked at vertical displacement of the finger?
Mm-hmm.
Is there anything in there?
Well,
so, for instance, speculating, a rising intonation, is the finger going to follow, moving up a bit? It was sparked off by Heriberto's and your discussion about intonation. I'm just curious, because just having a very flat horizontal line, that's probably difficult. So I expect,
yeah, absolutely.
Although on a very tiny scale, I expect at least some error on the vertical scale, but there could be some signal in the noise. So I'm very curious whether you have seen anything there.
Well, we had huge patterns of variations in terms of vertical drifts, especially with ASD children. Okay, especially with this type of children, with this type of populations, we had incredible variation in terms of patterns of vertical drift, and we were surprised by that. And actually, our clinical partners, sorry, our clinical staff were much interested in this kind of variations of patterns, because apparently the movement of the pattern movements of this type of subject is fairly peculiar, and so your observation and your suggestion is certainly useful, because you're making the connections with variations in terms of pitch, and in terms of body contours at vertical movements or vertical drifts in the figure movement. What we observed is that children with specific learning developments find it very hard to keep a straight line with a finger or his finger, and this is certainly a pattern worth investigating, because again, he points out a deep connection between movement and cognition, which is an interesting and yet unexplored, field area of investigation that could be tackled with this type of technology.
And is this purely line-based, or is there any modulation of this downdrift by punctuation marks? Because of course, intonation pattern over a sentence, usually your F0 goes down. So it could be a motor thing, but it could also be possibly, but I don't know how your sentences are positioned and so on and so on. But perhaps there is some much stronger link to a kind of downdrift of the F0 in your impaired populations. That is very speculative, but
yeah, I mean, your suggestion makes very much sense to me. Yes, but this is something we haven't explored yet.
Yeah,
but yes, it's very sensible, I think. Thanks, Aaron, for pointing this out. Yes, thank you.
Well, we will have further opportunities to chat about this.
Sure. I believe so. Yes, I agree.
Great. So I think that we're going close to the end. If there is no further questions or comments or something. Well, Vito, this is really great. Thank you very much for.
Thank you. Hope you enjoyed it.
Coming over. Oh, absolutely. I think it's fascinating. Really, it's all the opportunities and possibilities of this. As you said, rather simple techniques. I mean, it's just really fascinating. Thank you very much. And
thank you for your attention.
I hope you get your funding. That would be great.
For inviting me. Well, yes, actually, I mean, it would be a good idea to make it a kind of European project. I mean, at the moment, it's just a national project. So a kind of international project would be nice, because I mean, it's very cheap, and it would allow us to collect,
actually,
hundreds of thousands of subjects.
Absolutely, there was a question in the YouTube about the typologically diverse languages. So, for instance, if you have depending on the type of language, like a Finnish or Hungarian, you have this very morphologically complex words sentence. So who knows what is in a word?
That's true. There's very much sense. I mean, we don't have evidence about Finnish or agglutinative languages, but we have some interesting evidence about Arabic Semitic languages like Arabic and Hebrew, and apparently which are templatic languages with a high level of morphological complexity. And apparently we have very nice differences in speed birds, in connection with particularly complex morphological patterns. Yes, you're right. I mean, that's another fascinating issue with exploring with this technique. We're working on that. I mean, we have some evidence about to be published on Hebrew on that.
Oh, that would be great. So I'm sure you're going to need 3 fingers at least for Hebrew.
That's true. because because of diacritics, you know. You tend to raise your finger because you have diacritics on top of consonant patterns.
I was thinking of the Vinyam, you know, like
that's true. Right. Absolutely.
Excellent. Or Chinese, no, or this.
Or Chinese, That's a difficult question there.
Yeah, issues coming from whether the language is written from left to right, right to left, or even Maya script that it was in.
Down. Some of them are just vertically arranged instead of horizontally arranged. Yes.
Right. So and this has to do with handedness.
That's another issue worth exploring.
So what happens with handedness, right? So if you have Hebrew and you have, because I mean, obviously there is a correlation between language dominance and handedness. So and you are following your finger from in Italian or other languages, left to right. So what happens with left-handers, right?
I don't think there is any kind of strong correlation between the direction of your script and your handedness, actually. Okay. I mean, as far as I know, there is no such correlation. So So actually going through with your right finger, you know, from right to left, I think would eventually be simpler than in the other direction.
Yeah. Wow. That's interesting.
Okay.
Anyhow, well, thank you very much. Grazie, Vito.
You're welcome. Prego. Thank you very much for your invitation. It was a real pleasure to be here. Thank you very much for your attention.
And then please join to the next session. So it's in a month. So stay tuned. So we're gonna announce the next talk very soon. And then on that note, so thank you very much to everyone, to the technical team in Mexico City. We thank you also Sergio, who was dealing with the YouTube, and Harold and all the people. So we'll see you soon. Take care.
Instituto Nacional de Antropología e Historia.
Secretaría de Cultura.
Gobierno de México.